Howdy, howdy. This is Mr. Potter. We're going to continue our talk about different types of tests to determine when power series converge or diverge. Um, we talked a lot about the ratio test in our last lesson, and the main reason that we use the ratio test is not necessarily to see if a series does converge or diverge, but to determine the interval of convergence. And there's a lot of work involved with the ratio test. And so the idea here is that we're going to be taking a look at some other tests that are not necessarily as much work or as difficult of work to do. So we're going to start with the integral test, and we're actually starting from the perspective of the harmonic series. Which we've talked about in a couple of lessons. The series from n equals 1 to infinity of 1 over n. And we've talked about how this series diverges. But I want to talk about why it diverges. So I want to take a look at this, and I want to imagine when I look at this series, which is really 1 plus 1 half plus 1 third plus 1 fourth, and out towards infinity, I could think about this as 1 times 1 plus 1 half times 1 plus 1 third times 1, and so forth. And I could think of these as areas where I'm dealing with the height times the base. So if I wanted to get a picture of what this looked like, I could draw a height of 1 with a base of 1. Obviously, I'm not drawing my graph to scale. This next rectangle that I would add would have the exact same base, but would only be half as tall. The next one would be a third as tall as the original one. The next one would be a quarter as tall. And so what I end up with is I'm really finding the sum of these areas. But this looks an awful lot like a Riemann sum. And of course, if I was to compare this to a function like f of x equals 1 over x, my function would go through each of these points. And I could talk about the area under the curve from 1 to infinity of 1 over x dx, and that would be represented by the area under this green curve. You know, assuming that I'm actually going through all of these points on my graph. Now, this area that I'm dealing with this is actually greater than the sum from n equals 2 to infinity of 1 over n, because it includes this area, and it includes this area, and it includes this area. So this integral is strictly greater than this sum. And if I was to add 1 to this side over here and add 1 to this side over here, this side actually becomes n equals 1 to infinity, where this really becomes the integral of 1 over x dx plus 1 from 1 to infinity. But we talked about this in chapter 8, how anytime I'm dealing with an integral that involves infinity, I need to rewrite this as a limit. So I'm writing the integral from 1 to k of 1 over x dx. And I'm taking a look at the limit as k increases without bound. Now, I know that the antiderivative of this function is natural log of x, which I'm going to be evaluating from 1 to k as k increases towards infinity. But if I take a look at this, what I've actually got here is the natural log of k minus the natural log of 1 as k increases without bounds. But this goes to infinity. And so what happens is if the area under this curve goes to infinity, then the area under the rectangles, because this is something that's smaller than that, should also go to infinity. And so this is why our harmonic series diverges. So I can use this idea of an integral test, and I can look at particular functions that I can say if a sub n is really some function evaluated at a particular value of n, then I can compare the sum from n equals some value to infinity of a sub n. I can compare this with the integral from n to infinity of f of x dx. And the thing is, these are either going to both converge or both diverge. Now, the thing that's important to notice is that when I talk about this integral test, this idea that I could essentially replace a sigma with an integral sign, I'm doing two things here. One is that I'm harkening back to chapter 5 when we were dealing with Riemann sums. But the second and more important thing is that we're not talking equality. We're merely saying that they both converge to a constant value, or they both diverge. And so I want to go through several examples of this to kind of talk about it. Now we've already dealt with the sum of 1 over n, because what I'm doing here is if I take a look at this from 1 to infinity, I'm comparing to the integral from 1 to infinity of 1 over x dx, which we've seen several times, and it diverges. But if I was to take a look at the sum of 1 over n squared as n goes from 1 to infinity, I would compare this to the integral from 1 to infinity of 1 over x squared dx. And if I'm looking for the integral from 1 to k of x to the negative 2 dx, that's going to be equal to x to the negative 1 divided by negative 1. And I'm going to have to evaluate that from 1 to k. Of course, I'm interested in what's happening as k increases without bound. And so what I end up with is negative 1 over k minus negative 1 over 1. And as k goes to infinity, this term here actually goes to 0. And so this limit comes out to 1. Now when I say the limit comes out to 1, this sum is not 1. But this sum converges. And so all that I know at this point, I'm not saying what the sum is actually equal to. I'm just saying that the sum actually does converge. It actually comes to a particular value. So let's try the sum of 1 over n radical n as n goes from 1 to infinity. Now I should compare this to the integral from 1 to infinity of 1 over n radical n dx, or 1 over x radical dx. But I'm looking at this is really the integral of x to the negative 3 halves, which I'm evaluating from 1 to k as k increases without bound. But the integral of this is going to be x to the negative 1 half divided by 1 half, which means I'm really multiplying multiplying by negative 2. And I'm evaluating this from x equals 1 to x equals k as k increases without bound. So I'm going to have negative 2 over radical k minus negative 2 over radical 1. But as k approaches infinity, this radical function is asymptotic towards the x-axis, and so it becomes 0. And so this integral comes out to be 2. Now I'm not saying that the sum is not, I'm not saying that it's 2. The sum, as a matter of fact, is not equal to 2. But it converges. And I want to do one more example of this, because I'm starting to see a pattern here. If I look for the sum as n equals from 1 to infinity of 1 over radical x, I want to compare this to the integral from 1 to infinity of 1 over radical x dx. So I'm really looking at the integral from 1 to k of x to the negative 1/2 dx, the limit as x goes to infinity. But the antiderivative of this ends up being 2 square root of x, which I'm evaluating from 1 to k. And as x goes to infinity, my radical x function is an increasing function. And so this diverges, because I'm really going to be taking the square root of k minus the square root of 1. And as k goes to infinity, that's going to go to infinity as well. And so that means that the sum of 1 over radical n, as n goes from 1 to infinity, diverges. And so what I'm noticing here is, if this is something where after I integrate, I still end up with a negative power, I know that as my x value goes towards infinity, this graph goes towards 0. That's what happened here and here. But as I looked for this example here, where if I integrated, I ended up with a positive x power, then I end up with a function that's going to behave like a polynomial as x increases without bound. And so what we have next is something that's called the PTest, which is a simpler form of this integral test that we've talked about. But it's much easier to deal with. If I'm dealing with the sum from n equals some value to infinity of 1 over n to the p, this will converge. if p is greater than 1, and this will diverge if p is less than or equal to 1. So this is really nice because I know that if I was going to integrate this, I'm going to make this a negative exponent and then try and add 1 to it. Now, if this is already bigger than 1, I'm going to have an exponent that's smaller than the negative 1, and adding 1 to it is going to keep it negative. But if this was already less than 1, adding 1 to it forces it to be positive, and it means the integral would be an increasing function. And so this p-test is a real quick way of showing, just real quick by observation, it's converging or it's diverging. And we still have this case that we talked about at the beginning, because if p is equal to 1, then we're talking about the sum from n equals 1 to infinity of 1 over n, which is our harmonic series. And we know that that diverges. So just some real quick examples. I can talk about the sum from n equals 3 to infinity of 1 over radical n. I could even make it a cubed root of n. But as long as this power is less than or equal to 1, I can immediately say diverges. And I'm done at this point. I can say it diverges by the p-test. If I'm dealing with the sum from n equals 1 to infinity of 1 over n to the 5th, this converges by p-test. And so this p-test is a very quick test to determine it. But this p-test comes from the integral test. So if we didn't have the integral test, we wouldn't be able to just use this p-test just right off the top of our head. So that's the second of three tests that we're going to be talking about today. And the third test is actually going to use this p-test quite a bit. This third test is called the limit comparison test. And the idea here is that I want to take a look at the limit as n increases without bounds of the ratio of a sub n over b sub n. And there's going to be three possibilities here. One is that that's going to be equal to some constant. And if this is true, then the sum of a sub n and the sum of b sub n either both converge or both diverge. Which is really nice because I can take a really complicated series, like the series from n equals 6 to infinity of 3n minus 2 over 6n cubed plus 4n plus 7. And I'm thinking, oh, I'm never going to be able to deal with this. But what I can do is I can, let's compare that to 1 over n squared. And of course, I got this by looking at the difference in degrees. The dominant term in my numerator has degree 1. The dominant term in my denominator has degree 3. And I know that this converges by the PTest. Also the integral test, we did this earlier today. So if I look for the limit as n increases without bound of my term, divided by this term that I'm bringing up, of course, dividing by a fraction means I'm multiplying, that I'm really looking for the limit as n goes to infinity of 3n cubed minus 2n squared over 6n cubed plus 4n plus 7. And I can either use L'Hopital's rule or dominant numerator and denominator, top heavy, bottom heavy. I could divide through by n cubed. But what I notice is that this limit ends up being equal to 1/2. And the limit comparison test says that either both converge or both diverge. Well, I already know that this series converges. I chose it for this exact reason. And therefore, this series must converge. Okay? Now again, remember, I'm not saying what the series actually is equal to. I'm merely giving a thumbs up or thumbs down. Does it converge or does it diverge? So if I can ever take the limit of the same term and I get a constant, this constant could be 0, this constant could be any constant, but then that means that these either both converge or they both diverge. But if I ever get an infinity, in other words, if I get the limit as x as n approaches infinity of a sub n over b sub n is equal to infinity, and the series that I'm looking at is like the sum of b sub n diverges, then the sum of a sub n diverges. And this should look familiar too, because this is the direct comparison test that we were talking about before. Because I end up with a series that converges, and this series is top heavy, which means this series has more dominant terms than my known divergent series. That means A sub n must also diverge as well. So I want to go through some examples here. So let's take a look at the sum of n goes from 1 to infinity of 3n over 4n squared plus 5n. So I'm looking at this, and I'm not looking at it from the polynomial standpoint. I'm merely looking at the degrees. I see an n in the numerator, and I see n squared in the denominator. So I'm going to compare with the sum of 1 over n as n goes from 1 to infinity, because it has the same idea for the degree breakdown. The degree of the numerator divided by the degree of the denominator is 1 over n. But I know that this diverges. So if I look for the limit as n increases without bound of the original sequence, 3n over 4n squared plus 5n, and I want to divide by 1 over n, which means I'm multiplying by n over 1. So I'm really looking at the limit as n goes to infinity of 3n squared over 4n squared plus 5n. And this limit is 3/4. So because I'm getting a constant out of it, both have to diverge. Now, I already knew that this series diverged. This is something we've been talking about for the last week. But that means that this series over here, which looks a lot more complicated, looks like it might have a chance of diverging, because the terms are getting smaller. This one also has to diverge. So this limit comparison test is very similar to the direct comparison test that we were doing before, except I don't have to test the absolute magnitude. I'm really looking at the relative magnitude. I'm looking at the relative degrees. And I'm choosing these series based on what I know from the PTest. The PTest is my clue as how I'm getting those. I'm looking at the dominant terms in the numerator and denominator and trying to find a comparable PTest candidate. And the PTest is very simple. I can look at it, and by inspection I can tell if it converges or diverges. And I'm using those in my limit comparison test to make that work. So, thank you for watching. is Mr. Potter. Have a great day.